A2 Maths, Parametric Equations. Okay, so what I'd like you to do is just have a go at filling in this table of results, please. So a ball is kicked in the air, got its position vector recorded at certain times. So I have a quick camera that's recording the position of the ball at these times, starting from 0, 0.1 seconds, 0.2 seconds, and so on. And what it's noticed is the ball's position follows these two equations. The x value equals 2 lots of the time, and the y value equals 4 lots of the time minus 8 lots of the time squared. Okay, so just pause the video there and have a go at filling in that table yourself. Okay, so really it was just a case of putting these t values into both that equation. All right, so just doubling. That's why you can see that it's just 2 lots of it. So well done if you managed to get those results. And on this one, putting it in, a little bit more of a tricky equation, but still more than capable of filling in to get those results. Okay, so grab your new notebooks then, please. So what you've just done is you've just seen an example of what we call parametric equations. You had two equations to work out the x and y values using an extra variable, in the previous case, the letter t. So the letter t was an extra parameter. And because you had two equations linked by this common parameter, you had what's called parametric equations, hence the word parameter in there. Okay, so let's have a look back at that example just to show you what I mean. So x is equal to 2t, y is equal to 4t minus 8t squared. And in that case, you can see that you've got this extra parameter, in this case, t. Now that variable t could be absolutely anything you like. It doesn't have to be t. You'll see some examples later where it's a theta value, as if it's linked by an angle. It can be any sort of extra variable you like, as long as it appears for both the x value and the y value linked by this new parameter is what's called a parametric equation. So in that case, it's defined by the letter t, where t is the parameter. Okay, so pause there, get down what you need. Okay, so what I've done for you is I've just filled out the grid with a few more numbers. So I've filled in some of those extra gaps. And the reason for that is because what I'd like you to do is just plot down on a Cartesian grid. In other words, with x going along the bottom and y going up the side. So a normal sort of grid that you're used to on squared paper, going from 0 across to 1 and from 0 up to at least 0.5. Okay, and then what I'd like you to do is just have a go at plotting x against y. You can completely ignore t now. We've used t to get the x and the y values of that. If it's in the previous examples of football, the football at certain points. So the t's been used. We can ignore it. We can ignore the equations. I just want you to plot those two things. Okay, so pause it there. Have a go at plotting it. See what you find out. Okay, so hopefully if you plotted it, then you realise quite quickly that what you were plotting was a quadratic curve. You can see that it formed a nice quadratic curve. So these two equations, these parametric equations, actually formed a quadratic curve. Now, if it's a quadratic curve, it means we should be able to find out the equation of this quadratic curve. Okay, so again, forget the equations, forget the data now. Just looking at this equation here, this graph, how would you go about finding out the equation of that graph? Okay, so to find the equation of that graph, what we really need to do is see if we can figure out the roots of that equation. Now we know the roots of the equation because we actually plotted it. 0 got 0, 1 got 0. So it's got two clear roots at x equals 0 and x equals 1. So if I know two of its roots, I can now write the quadratic equation. And you'd be right in thinking it should be y equals x minus 0, x minus 1. But be careful, okay? Because if you just did x minus 0 and x minus 1, that doesn't account for how high it is. So you've got to make sure you've got the extra variable. It should be a lots of x minus 0, x minus 1. And so because we've got those roots, we can write it in this form. Notice that x minus 0 is just x minus 1, because you've got the factor there. How do I go about finding this a value? Well, what I need to do is just see if I can find any coordinate, x and y. So in the case here, I'd go for 0.5 and 0.5 and substitute it in. So if I substitute in 0.5 in there and there, I've got 0.5 times minus 0.5, which gets me a quarter. 0.5 equals a quarter A, so a bit of rearranging, A equals minus 2. Notice you can neaten this up if you wanted to. If you took the minus inside this bracket, you could rearrange it to 2x lots of 1 minus x. And that'll be important in a minute. So 2x lots of 1 minus x if you wanted to neaten it up. Okay. So obviously that's not the best idea. Being able to plot a graph and therefore get the Cartesian equation isn't going to be the best and the most efficient way of working out the Cartesian equation from having the parametric equations. So what we're going to do is we're going to look at how to do it without a graph. So what I'd like you to do, please, again, just grabbing your notebooks, write down the parametric equations that you can see in front of you. And what we're going to do is we're going to see if we can get that Cartesian equation by using substitution. So I know, because t is a common variable for both of these things, what I can do is just take in this first equation, I can rearrange and make t the subject. So in this case, t could equal x over 2. So I'm rearranging it and I'm going to make t equal x over 2. Once I've made t equal x over 2, I can take that t value and I can now substitute it back into this equation. And the moment I do that and cancel out the t and get this equation, I've managed to get my Cartesian equation. So there we go. I've found the Cartesian equation. It's not linked to the extra parameter t now. It's just a link between y and x. So obviously that's not the neatest version of it. I could neaten this up a little bit. 4 over 2 is going to be 2x. 8 over 2 squared is 4, so 8 over 4 will get 2x squared. And so I could write out my equation like that. A little bit of factorising. I can see 2x is common in both. Hence the equation 2x lots of 1 minus x, which as you saw is exactly the same as the previous example. So without having to sketch it, I've got down to the same equation by using the parametric equations. In the previous example, it was minus on the front, but these two were in the opposite way around. So it was the same equation. Okay, so now you know that, what I'd like you to do, please, is see if you can work out the Cartesian equation of those parametric equations. So x equals 2 sine theta and y equals 2 cos theta. So just have a quick think about it. Pause if you want some more thinking time. Okay, so if you did what we did previously and you rearranged this x equation, you took the 2 across, x over 2, you did sine to the minus 1 and you got this, you'd be correct. When you substitute that into this equation, you end up with that. Now that is a correct example of a Cartesian equation. The problem with this Cartesian equation just here is because you're using the inverse function sine to the minus 1, you are restricting your domain and therefore your final answer is restricted. And also if I asked you what graph does that look like, if I asked you to plot that, what would it look like? I wouldn't expect you to know off the top of your head what that looks like. Okay, so there's got to be an alternative approach to being able to do parametric equations when they involve angles. So whenever you see angles in parametric equations, you need to get into the mindset of thinking, I'm going to use some sort of trig identity to link these two together. So you should be thinking, because I've got sine theta and cos theta, can I think of an appropriate trig identity that links sine and cos? And hopefully, as you know, the most obvious one that links sine and cos will be sine squared plus cos squared equals 1. Sine squared plus cos squared equal 1 can be used to simplify these two equations and make them into a Cartesian equation. So what I'm doing is I'm just rearranging to get sine squared. So how can I do that? I'm just squaring everything. So 4x squared is obviously x squared, 2 squared is 4, sine theta squared is sine squared theta. I could do the same for y. All right, nothing wrong with that at all. I'm allowed to do that because I'm squaring each of the elements. And so therefore I've got what x squared and y squared is. Now I know what x squared and y squared are, I could use sine squared plus cos squared equals 1. And there's absolutely nothing wrong with you rearranging these, writing it as x squared over 4 equals sine squared theta and substituting it in, or writing it as y squared over 4 equals cos squared theta and substituting it in there. And if you do that, it means that you can then neaten this up. You'll get x squared over 4, y squared over 4 equals 1, and you can neaten it up by timesing by 4. Another idea though is because I've got 4 sine squared and 4 cos squared, why don't I just times everything by 4? If I do that, I end up with this equation. So 4 sine squared theta, 4 cos squared theta equals 4. And from there, what I can do is I could just substitute my values in straight away. So I know that 4 sine squared theta equals x squared. So that's going to be x squared. 4 cos squared theta equals y squared. So that part there will be y squared, and I end up with that equation. And I ask you the same question again. What does that graph look like? What does x squared plus y squared equal 4 look like if you plotted it down? Now, I'd expect all of you out there to be able to say it's going to be a circle, centre 0, 0, radius 2, because it's 4 square rooted. So you can tell straight away from that what the equation looks like. This equation would have plotted a half circle, so therefore it wouldn't have covered everything. And again, I wouldn't expect you to know that just by looking at it. But it's interesting to see that the parametric equations, x equals 2 sine theta and y equals 2 cos theta, are exactly the same as a circle of radius 2 at the origin 0, 0. Okay, so the key factor there is making sure you do this. If you have parametric equations involving trig functions, you should always try to use trig identities. All right, that should be your first thought and the first thing you go for. Okay, pause if you need more time to take some notes down. Okay, so let's have a look at an exam question then. So just grabbing your notebooks, write that question down, and I'll give you an opportunity to do it yourself. So just pause there, write the question down, and see if you can do it yourself. Okay, so let's see what you did then. So first thing I noticed is you're looking for where they intercept. So there's 2 lines here. You've got this equation, which looks to me like it's going to be some sort of quadratic curve, crossing this straight line. So what you can do is you can replace, you could either write this in the form y equals x, you could write it as a Cartesian equation and then substitute it in, or because you know what x and y are, you could substitute them straight into there. There's absolutely nothing wrong with you doing that. When these two cross, the x value equals 3t, so that x value there will equal 3t. When these two lines cross, the y value there equals t squared plus 2t, so I can replace it into there. And that's the easiest and most efficient way of solving an intercept between a parametric and a Cartesian, just substituting them in. So what do I end up with? 3y equals obviously x plus 6, that's my starting position. I take that y value and I can substitute it in first. I can then take the x value, which is up there, 3t, and substitute in there. So I've replaced the y and I've replaced the x. What does that mean? Well, now I can expand it, and you notice there is only one variable in it, which is a t value. So I can expand it, I can neaten it up, I can see I've got a quadratic, and that will allow me to work out the t value for when these two lines cross. So t equals 1 and t equals minus 2. So if you think of t as a time, what time do they cross? At 1 second and at minus 2 seconds. So you could see how they might use this in an applied maths question. Right, so what can I do though? Because that's not quite answering the question. Where do they intercept? I need the x and the y value. I can take those two and substitute them back into this equation just here. So when t equals 1, x is going to equal 3. And when t equals 1, y is going to equal t squared plus 2t, which is also 3. When t equals minus 2, what do I get? Well, x is going to be 3 lots of minus 2, so that's minus 6. And y is going to equal t squared, which is going to be 4, minus 4, which gets you 0. So you can work out the points when they cross using those two. And a quick check, is it true? Well, 3 times 3 is 9. 3 plus 6 is 9. Definitely correct. 0 and minus 6. So 3 times 0 is 0. Minus 6 plus 6 is also 0. Big tick, also correct. Okay, so just to write the answer down at the bottom. Okay, again, pause if necessary, just to give you as much time as you need before we move on. Okay, so plenty of work to be getting on with. So what I'd like you to do then, please, is just have a look at those exercises. And as your teacher and myself have said before, just have a look at those exercises. You don't need to do every single one of them, but it'd be a good idea to make sure that you do enough so that you really do understand how to change parametric equations into Cartesian equations. Okay, so let's start the lesson off with just in your notebooks. And what I'd like you to do, please, is just get that exam question down and then just pause it and have a go yourselves. Okay, so let's see. So the curve is defined by the parametric equation x equals t plus 1 over t, y equals t minus 1 over t. So they're giving you a parametric equation, and what you're trying to show is that it can be written as x plus y times x minus y equals 4. Okay, in Cartesian form. So they're giving you a big hint on how to write this in Cartesian form. And it's not something you just jump to the conclusion. You try simplifying these, you'll notice that you can't easily make t the subject and therefore substitute it in. So they're giving you a big hint here. So what I'm doing is I'm just going to think about maybe rewriting this. So if I rewrote this, I'm thinking maybe x squared, maybe an xy in there, maybe a minus y squared. So what I'm going to do is just work out what x squared and y squared actually are. So x squared will be t plus 1 over t times by t plus 1 over t. So I can see I get a t squared, I get plus 2, because I'm going to get t times that is 1, that times that is also 1, so that's 2, plus 1 over t squared. For y squared, I get exactly the same, but I get a minus in the middle, okay, and then the end is the same because it's minus times a minus is a plus. So there we go. I've got my x squared, I've got my y squared. So I know that if I expanded these, I'd get an x squared and I'd get a minus y squared. What I also do is I notice that x squared minus y squared is a difference of two squareds. So really, x squared minus y squared, I could write like this. T squared, which is just that one, take away that one. And what does that become? 4. But what's another way of writing x squared minus y squared? Well, I could write that in the case of this one, x plus y and x minus y. So using the difference of two squareds, x plus y, x minus y equals 4. The other options, in case you didn't notice it's a difference of two squareds, would be just to expand this and substitute it in, or even just substitute them straight in. So if you substitute them straight in, for example, you would get t plus 1 over t there, plus t minus 1 over t there. The two t's would cancel out. Sorry, the two 1 over t's would cancel out in that case, and you're left with 2t. On this one, you'll be doing the same sort of idea, but you put t plus 1 over t in there, minus t plus 1 over t in there, and then you end up with just 2. And then you, as you can see, 2 times 2 equals 4. So there's nothing wrong with you substituting it in there, as long as you don't use the 4, because you are trying to show that that will equal 4. That's what you're trying to show. It's more normal for the examiner maybe to put a C value or a K value in there and expect you to calculate that value. Okay, so I know the curve is defined with those two equations. And what I'd like to do is find the gradient, dy over dx in terms of t. Okay, so I'm just going to pause there. I would like you to have a go at working that out using your skills of rearranging a parametric equation into a Cartesian equation. Okay, so let's see how far you got. So the first thing you should be thinking about is rearranging the x equation, maybe taking away 1, dividing by 3, and substituting that back into this one. So therefore, straight away, sorted, I've got a Cartesian equation. Now what I need to do is think about how to differentiate it. But I'm going to make my life a bit easier. I'm going to sort this out and neaten it up because I could do x minus 1 squared over 9, and I could do 4 lots of x minus 1 and divide it by 3. So I end up with this equation. So just make sure you're happy with that if you didn't do it before. Okay, right, now can I work out the gradient function? Yeah, because it's just dealing with x squareds, x's and numbers. So I can deal with it quite easily. Bring the 2 to the front to get 2/9 x plus 10 over 9 on that part. And there we go, done. Or 2x plus 10 over 9 if you got it like that, it's the same thing. So you can work out the gradient of parametric equations by converting them into Cartesian and then differentiating normally. And sometimes that is an efficient option. But as you know also, sometimes you can't do that. You can't simplify these things by substituting them in, like we saw in the previous example. So we also need to have an alternative method of being able to differentiate it. So let's have a look at that then. Oh, terms of t, excuse me, I didn't quite finish it because it does say it there. Because we haven't got it in terms of t, what is the x value? The x value is 3t plus 1. So yes, you should have finished it off quite correctly by substituting that 3t plus 1 back in for x, and therefore you've got the gradient function in terms of t. So you could find what is a gradient at t equals 1, for example. Okay, neaten it up gets you 2t plus 4 over 3. Okay, but as we did before, it's not efficient to be able to just do this. There's got to be an alternate way as well. Now, the alternate way is by using chain rule. So what we're going to do is just grab your notebooks, differentiation with parametric equations, and we're going to look at how we could potentially use the chain rule to differentiate. So what we want to do is we can do that. That is an option. Changing it into a Cartesian equation and then differentiating using your normal skills. Nothing wrong with that at all, as long as you can differentiate it, or if you can't think of how to differentiate it using chain rule. Okay, right, but let's have a quick look at how you do it with a chain rule, because you need to make sure that you're efficient with both methods. So if we want to differentiate it using the chain rule, what we notice is that dy over dx can be split up, and we're allowed to do this. This is what we usually do. We usually make the inside function u, and then we work out du over dx, and then we work out dy over du. So we have dy over du and du over dx. That's how we usually use the chain rule. So what I'm doing in this case is I'm just showing that we can split dy over dx up into two functions, dy over dt and dt over dx, where that would be my inside function and that would be my outside. But realistically, when you look at it, you can see that the dt's cancel out and you're left with dy over dx. That's how technically it works. So we can cancel those two out, leaving you dy over dx. Right, so if that is the case, why does that help us? Well, dy over dt means I'm just going to differentiate the y function in terms of t. So I know that y is usually in terms of t, so that's really handy. This one's a bit of a pain because this is saying differentiate the t equation in terms of x. So I need something like t equals 3x plus x squared. I don't usually get that. I usually have it the other way around. X equals some amount of t. But I can get around this. I can rearrange dt over dx to dx over dt, but if I flip that fraction round, I've got to make sure that I flip that sign. So usually it's standard to write it like that. So make sure that's nice and neat in your notebook, because that's the rule that you will generally use. If you want to find the gradient function y in terms of x, you differentiate the y in terms of its parameter, and then you differentiate the x in terms of its parameter, and you just divide one by the other, making sure you do numerator over denominator. Okay, so pause if you need some more time. Okay, so let's go back to that previous example, and instead of making it into a Cartesian differentiating it, we're going to use the chain rule. So the chain rule says I want to work out what x is in terms of t. So I'm going to work out dx over dt, and I can see quite clearly that's just going to be 3 because it's 3t. I also going to work out dy over dt, and that one just as easy, 2t plus 4, done. Now if I want dy over dx, there's the dy, the dx is in the wrong place, but I can easily work out dt over dx. I can do dt over dx, or I could just divide. So my two choices are rewrite it as dt over dx is a third and then just put them together, or using this equation just do dy over dt as the numerator, 3 as the denominator. So if I want to write it in terms of t, 2t plus 4 divided by 3, which of course is 2t plus 4 over 3. Exactly the same as the previous one, but look how more efficient that is without having to change it all into Cartesian and then change it all back again at the end. Okay? Make sure you're aware of both options though, because sometimes the calculus can be really messy if you're using this sort of idea, and if you change it into a Cartesian, it can be really easy. Okay, so grab your notebooks, get this equation down. Let's have a look at how we do a question to do with equations of tangents, with parametric equations. Okay, so you probably want to go yourself. So write it down in your notebook and then have a quick go yourself. Okay, so let's see how far you got then. Now, if I see the words equation of a tangent, I know that the equation of a tangent is the equation y equals mx plus c. So I know that m is going to be the gradient, c is going to be the intercept, or I could do it in any of the forms. What's important though is that I know that the equation of tangent is a straight line. So what I'm going to do is I'm going to work out the gradient function. I'm also going to work out my y and my x value at the point of my tangent, and so therefore I can work them all out by substituting them into the equation of a line. So the first thing I'm going to do is I'm going to work out the x and the y value at the tangent point when t equals 1. So if I do that, x equals 8 and y equals 4. Okay, so you could do these in either order. So I've started off by just working out the x and the y value. So I know whatever my curve looks like at the point when 8 and 4, I'm looking for that, the tangent at that point on the curve. Right, what else do I need then? So I've got an x and a y value. That's going to help me work out my c, or I could just use those straight away in the equation of the line, which is y minus y1 equals m lots of x minus x1. I could just use these 2 points. What else do I need? I need the gradient. So that's what I'm going to do next. I need the gradient function so I can work out the gradient at any given point. How do I work out the gradient? I'm going to use the chain rule. So I can work out dx over dt is just going to be 6t. dy over dt is just going to be 4. And I do dy divided by dx. So it's going to be 4 over 6t. Now 4 over 6t simplifies down to 2 over 3t. So it's dy, which is the 4, divided by the dx, which is the 6t. Right, so that's my gradient equation. That works out the gradient at any given point t. Now I want the gradient when t equals 1. So that's what I'm going to work out. When t equals 1, my gradient is just going to be 2 over 3t, which gets me 2/3. So now I know my gradient, and now I know my x and my y value. I can straight away write the equation for the curve in that sort of format. And there we go, y minus y1 equals m lots of x minus x1. All right, it doesn't dictate what form they want the equation of the tangent, so that's perfectly reasonable, just like that. Okay, you guys that have got y equals mx plus c, then yes, you've got 2/3 x, you can see that, and then you've got 2/3 times 8 plus an extra 4. Okay, and yes, you can sort that out yourself. All right, or you can write it in that format as well, of course, which is probably the neatest in this case. All right, okay, so what I'd like you to do, you've got 2 exercises there to have a look at. Same as what I said before, making sure you take your time and work through some of those examples so that you really sort of solidify how to do differentiation with parametric equations. Okay, so let's move on to integration with parametric equations then. So as you can see here, we're being asked to integrate y in terms of dx. That's a standard sort of way of writing it. Normally though, the y value, we write down the equation, for example, 3x squared plus 2x plus 1. So normally the y value is filled in, all right? But I'm just showing you that's what we usually have to work out. The integrate the y equation in terms of x. Now the problem is, when using parametric equations, the y value is in terms of the parameter, in this case t. So there's no point in me substituting that straight in and doing it straight away, because this is integrating in terms of x. So let's have a look. Grab your notebook, make sure you got the question down. Let's see how we should go about doing it. So the first thing I want to do is substitute that y value in. Nothing wrong with doing that. Okay, that's correct. But What you can't do is then go on and integrate it, because that's the variable t and that's the variable x. So we can't integrate it just yet. So what we're going to have to do is somehow change this dx to dt. If I can change that dx to dt, then I should be able to work out the integral in terms of t. Now, what's the link between dx and dt? The gradient function dx over dt. So if I use dx over dt, which is in this case going to be just 5, so I've worked out my differentiation of x in terms of t is just 5, then I can work out what dx is. So in this case, I can see that dx equals 5 dt. Why does that matter? Because now I can replace that dx by 5 dt, which is what I'm going to do. And now I'm in a position to do the integration because I'm dealing with 10t squared, all right, dt. 2 times 5, 10t squared dt. What does 10t squared go to? The power increases by 1, so it's 10t cubed over 3. So that's where this part comes from, 10t cubed over 3 plus the constant of integration. And if they want it in the form x's, then of course you can rearrange and substitute that back in. But there's no reason for them to do that. Okay, no reason for you to do it automatically. But you can rearrange it, you can write it in the forms of x or y if you needed to. Okay, so still sticking with your notebooks, have a look at that exam question and we'll have a look at solving that. Okay, so this is going to be an example of, in some cases, be careful what's not to do. Remember that when you come to doing integration or differentiation, you have two options. You can either use the differentiation integration with the parametric equations, or you can change them to Cartesian and work them out. Now we know that if I was going to change this to a Cartesian equation, in this case, then I need to do something, maybe linking the sine squared and the cos squared together. Okay, but the example I want to look at first is if you didn't do that, if you did it with parametric equations, just to see the difference. Both answers get the same answer at the end. Right, you need to know both skills. So pause there, get down what you need, have a go yourself at doing both methods if you want to, and then we'll have a look and compare the two techniques. Okay, so the area bounded by the curve, the x-axis, and the line x equals 3 and 5. So just to get your head around what that means is, if you imagine this is our curve, this is the x-axis just down here, so that's my x-axis. All right, go along there. The x equals 3, so there we go. That's going to be the point when x equals 3, and the point when x equals 5. So there we go. That's the point x equals 5. So we're looking for the area under the curve, above the x-axis, and between the lines 3 and 5. So all of that is a flash way of saying, can I find the integral of the x equation, okay? So the y equation, as we usually do, in terms of x, because we're looking at it along the x-axis. So can I integrate y in terms of x between the limits 3 and 5? That's basically what it's asking. Okay, right, so let's get rid of this and let's have a look at how we go about doing it. I'll point back on, there we go. Right, so first find the values of dx in terms of d theta. Okay, because I want to work out the integral of y d theta. So I'm going to work out dx over d theta. I can do that using my skills of differentiating cos 2 theta. And I know I can bring the 2 to the front. Cos goes to minus sine, so therefore dx over d theta is minus 10 sine 2 theta. A little bit of rearranging tells me that dx is going to equal minus 10 sine 2 theta d theta. Okay, why does that help me? Because now I've started to work out the integral of y dx. I know what y equals in terms of theta, it's just that. And I know what dx is in terms of theta, it's just that. So I can fill both of those bits in and just make sure you're happy. There's your y value and there is your dx value. Right, so why does that help me? Well, what I can do now is I can multiply these out to get this, and therefore I should now be able to integrate it. But it's not the most easy thing to integrate. So just check you're happy where that's come from. 3 times that is minus 30 sine 2 theta. 4 sine squared theta times by 10 is going to be this. But of course, these two parts can go together. All right, sine squared times by sine, both 2 thetas, I can put those together to make sine cubed. Okay, now what I'm doing is I'm just trying to make my life a little bit easy for myself. You don't have to do this, but I'm just simplifying it. I'm putting the minus part second. I'm putting the 40 and the 30 are just numbers outside the integral. So really, I'm dealing with the integral of sine 2 theta, and I'm dealing with the integral of sine cubed 2 theta. So I've got 2 things to deal with. That one, I would say, is quite easy. Okay, the integral of sine 2 theta, as you know, is just going to be the 2 would go underneath, so it's half sine different integrates to minus cos. So that bit I could deal with no problem. This one's a bit of a pain though. So let's have a look at a technique how to do that. Now it's quite likely in your exam that you would have already been given some hints on how to integrate sine cubed, but it is a good opportunity to go through how to integrate sine cubed 2 theta anyway. So even just as a standalone, it's important to know the techniques to deal with this because it's not obvious what you should do first. You would be given that in an exam, okay, that hint, that if I want to integrate sine cubed 2 theta, I could use some sort of trig identity approach, or if you've been given this as a hint, they're basically saying to you, this is the easy way to do it. Now it's not obvious because I haven't made an error there. I have meant to do cos 2 theta, even though the question itself is dealing with sine 2 theta. So let's just go with it and just see what this integral of sine cubed 2 theta goes to. So I'm taking this hint, I'm doing what I do normally, I'm going to work out what d theta is. And when I differentiate it, I get du over d theta, great, equals minus 2 sine 2 theta. So the cos goes to 2 theta. Now, in fact, that and that might cancel out slightly. So I can see that when I rearrange it, I get d theta equals 1 over minus 2 sine 2 theta du. Now let me just put that back in. And when I put it back in, I realise that some of these cancel out. So that cubed and that one will cancel each other out. The minus a half I'm stuck with, so we'll take that out. But I end up with just sine squared 2 theta du. The problem is I still can't use my substitution. So I'm still stuck with the theta and a u because I've got cos and that's sine. But now that it's squared, it makes it very easy for me to use an obvious trig identity. Sine squared 2 theta is the same as 1 minus cos squared 2 theta. Okay, because sine squared theta plus cos squared theta equals 1. Sine squared 2 theta plus cos squared 2 theta equals 1. Doesn't matter about this part. Okay, right, that I can integrate because 1's just going to go to u in this case. Cos squared 2 theta is u squared. So really, I could just write it like this. Now I'm allowed to use my substitution. And what's the integral of this? Well, 1 goes to u and u squared will go to u cubed over 3. Okay, so 1 goes to u and that goes to u cubed over 3. And there we go. I've finished my integration of that section. I've got 40 lots of it. So the 40 and the minus a half is going to go to minus 20. And this one I can deal with quite easily as well, because it's just going, like I said, it's going to go to minus a half cos 2 theta. Okay, so that's what that part goes to. Now I've substituted in back into the u value, which is there. And now that I've got that, I can rewrite my equation. I can write my full equation. So I've substituted in that bit of the integration. This part here is going to go to minus 30 lots of minus a half cos 2 theta plus c. And I can neaten this all up. Okay, so yes, it's quite big. It's got a lot of work in there. Okay, but you've finally got all that integration. And as I said already, that might be section A to the question, and then they might have given you this as section B. So therefore, they've already given you lots of hints to get down to there. Okay, so what do we need to do next though? Because we haven't quite finished. We haven't used these 3 and the 5 values. We can actually simplify this out, because I can see that the minus 20 lots of it there and the plus 15 lots of it there cancel out. And I've now done my integration. So I've sorted out the integration, but now I can sort out this area part of the question. So I got the area between 3 and 5. I've already done the integral, so I know what the answer to that is. It's going to be all of that equation between 3 and 5. The c value's gone, of course. Right, be careful. It's very easy just to stick the 3 and the 5 in, but you need to notice, especially where I've written it, is that when I integrated this in terms of x, your x values go at the end. So x equals 3, x equals 5, not your theta values. You've got 2 choices now. You can either change the theta values here into x's, or you can change the x values here into thetas. It's up to you which one you do. They both work. Sometimes one's easier than the other. So for example, if I want to change the values of theta when x equals 3 and 5, what I'm going to end up with is, by substituting that back into there, rearranging it, so you can see I've got 3 over 5 cos to the minus 1 and then a half from the 2 theta, and put the 5 in gets me that. So that's one option. All right, I could use those 2 theta values and substitute them in there. The other option though is to convert these two in terms of x. Now they actually look quite nice. Look, 5 cos 2 theta is just x. I could rearrange this one as well. All right, cos 2 theta is x over 5, so I could substitute both of those in. And this one just seems a little bit easier. Okay, so I'm rearranging my x equation. I'm going to substitute it into there, and I'm going to end up with that equation like that. Right, why does that help? Now that's x and that's x, I can just put my numbers in. Once I've neatened it up slightly, made it a bit easy for myself, and lo and behold, 242 over 75. So that's a big question with a lot of work. Okay, so there is a lot of things going on there. It's more likely in the exam you'll be given lots of steps on this, more broken down, and certainly some hints on how you should go about doing it. Okay, but as I said when I first did this question, there was 2 options. One option is what you just did, which is using integration with parametric equations. The other option is thinking about how to write it as a Cartesian equation and then just integrating it, integration of y dx, same as what you would do normally. And let's just have a quick look at what happens if you tried using that technique. Okay, so you got the equation. First thing I want you to do is just try writing it as a Cartesian equation. So pause there and see if you can work out the Cartesian equation for x equals 5 cos 2 theta and y equals 3 minus 4 sine squared 2 theta. Okay, so because we've got cos and because we've got sine, you can be thinking about the same function that you did before, which is sine squared plus cos squared equals 1. Luckily, I've already got sine squared. If I get this to cos squared, that makes life a little bit easier. So a little bit of rearranging. Cos 2 theta is just going to be x over 5. So therefore, I know that sine squared 2 theta can be rearranged to 1 cos squared 2 theta. So this is the option I would pick. I could rewrite that as 1 minus cos squared 2 theta. Oh, but look, cos 2 theta is just x over 5. So really, y is just going to equal 3 minus 4 plus 4 lots of cos squared 2 theta, but cos squared 2 theta is just x over 5. So that neatens that up slightly. Okay, I could rewrite it as 4x squared over 25 minus 1. But what I want to do is I want to work out the integration from the previous one. So if I want to work out the integration from the previous question, which is between 3 and 5 for y dx, I could just literally put that into there, get the answer straight away. All right, you can even do that on your calculators. The integration of 4x squared over 25 minus 1 between the limits 3 and 5. Job done. And as you can see, that's literally a few steps. So sometimes converting it into a Cartesian equation is a lot more efficient than all those steps that you did previously. Now, those steps you did previously, you may have to do in your exam. So it's not a case of saying I just couldn't do it, so therefore I'm not going to. You may need to do those in the exam. But also, looking at the amount of marks a question's worth dictates on whether you're doing too much work. So if this question's only worth a couple of marks and you're spending all that time doing that big long integration, you probably should think, can I convert it into Cartesian? Is that going to be easier? In this case, yes, it is. Right, so do have a go at looking at integration of parametric equations. Have a look at exercise 8.1 on page 353 before you move on to the new lesson.